All right, welcome back. Let's now talk about conditional probability for two events, A and B. The probability of A conditioned on B is the probability of A intersect B divided by the probability of B, obviously, for probability of B greater than 0. Okay. You have definitely seen this equation before. You're quite familiar with it. What we are going to do now is to try to think about this a little bit in a different way from the perspective of the relative frequency of things. You could think of probability as the relative frequency of something, right? If any of you like basketball, we are talking about a specific basketball player, and his shooting percentage is 30% on 3, which is terrible, but okay, 30%. So from the perspective of the relative frequency, this player, when he shoots 1,000 times, he's going to be scoring on average around 300 times. This is the relative frequency of an event. So we'll try to look at this from the perspective of the relative frequency. And from that perspective, it is the relative frequency of the event A intersect B in experiments where B occurs. What is this mathematically? It is N A intersect B over N B. Have your random experiment. You perform it a total number of times, say N. You have a specific number of times where B occurs. You have the relative frequency for B. Now you are thinking about the relative frequency of the event of A happening with B under the situation that B happens. Let me just, excuse me. All right, how can we convert this thing into probability? How can we get from here to here? Yeah, well, that was not the goal. Yeah, obviously, yeah, to do the general probability thing, in order to get the number exactly, you would need n to go to infinity. But n doesn't appear here. How can we make this like this? How can we convert this alone into probability, this alone into a probability?
Probability of A intersect B over probability of S is the frequency. Yeah, but true. Logically, you are right. This probability of S you are talking about would be reflected to what? To the division by all possible outcomes, right? So that's how we convert it. It's you divide by n in the numerator and denominator. This becomes a probability. This becomes a probability. As n goes to infinity, obviously. But at least it gives you the same intuition, right? Okay. A well-known rule is that the probability of A intersect B is the probability of A given B times the probability of B, which equals the probability of B given A times the probability of A. Okay, let's do an example. Example 1 is on the binary symmetric channel. We will leave the concept of probability a little bit and talk about something a lot broader. I mean, what is this channel means? What is that? Okay. Any of you took digital communications course? Is it because it is still you will take it in the future? It's like for the, okay, tell me that. Okay. So this concept of channel, the entire modeling of data transmission, data communication, and data storage is like that. You have a transmitting side or a writing side.
You have an imperfect channel that corrupts part of the data with various sources of noise to corrupt parts of the data, and then you have the receiving end trying to understand what was transmitted by the transmitter under zero error. This is always the fundamental problem of wireless communication. And it is quite astonishing to think about that all of these research papers and wonderful results and books, you could think of all these models without an exception the same way. But the complications happen because of the nature of the channel. Transmitter, imperfect channel, receiver. Okay? Obviously, we will not really talk about the most advanced channel models or anything. We will talk about very simple channel, which is the binary symmetric channel. We have the input here. We have the output here. And then we have some probabilities there. You are very smart students, and in general, I don't like the strategy of asking students to memorize something, but it's like a self-check to think about this. These probabilities on the edges are always the probability of output given input. Output given input. So you receive a 0, given what was transmitted is a 0, probability 1 minus p. You receive a 1, given what was transmitted was a 0, P, 0, 1, P, 1, 1, 1 minus P. So these probabilities, if we can put them like this, these probabilities are always probability of output conditioned on input. Let's change the mark of conditioning and make it a standard one. Okay? Good. So this binary symmetric channel we are discussing is characterized as follows. AI, event input is I, BJ, event output is J, error happens with P, and the probability of A0 is 1 minus delta. The probability of A1 is a delta. What is the question right there? It is that we want to find the probability of the intersection AI intersect BJ, which can also, by the way, be written as this, AI and BJ. So normally I exchange this notation, so don't get confused, please. For all I and J. All right, solution. This probability, the probability of AI intersect BJ, is the probability of BJ given AI multiplied by the probability of AI. You want to get a specific probability. The way you go about this probability is you go for the equation that is based on the ingredients you have in hand. That's how we do it. For example, if we switched it to AI given BJ times probability of BJ, do we know AI given BJ? This is the wireless communication problem, right? That you stay at the receiving end, you get some data, and you want the probability that this data was something. So yeah, of course, there should be some more effort to get this probability. But we know this probability, and we know this probability, all right? And by the way, well, we will talk about this later, but remember that this probability particularly is called the a priori probability in wireless communications and data storage. A priori probability means the probability is before transmission, before you transmit, all right? Good. We will not go through this example in deep details, but what is the situation under which this probability is 1 minus P and the situation under which this probability is P? Let's start with this one. Thank you. I equals j. I does not equal j. Right? When you are here or here, it's 1 minus p. When you are here or here, it is p. Good? The rest is just some substitution, so we will not really do it. I'll leave it for you. Okay, total probability theorem. Suppose B, K in 1, 2 to n are mutually exclusive such that the union of bk, k from 1 to n, equals S. So bk, this bk thing, is a partition of S. Let's try to look at it on some Venn diagram. As if you have B1, B2, B3, B4, B5, and B6. B1, B2, B3, B4, B5, and B6. So, thus, or then, the probability of A is summation from k equals 1 to n, the probabilities of A conditioned on bk times the probability of bk. Let's assume that A looks like this. Any ideas how can we prove something like this? How can we decompose? Bless you. How can we decompose A?
Is the union of intersection.
Exactly. Thank you. So A is the union from k equals 1 to n. A intersect B k. Good. What do we know about these events? They are mutually exclusive, and thus the probability of A can be easily shown as the summation from k equals 1 to n, the probability of A intersect B k. How can we decompose this such that we finish the proof? Which is still on board? Right? Correct? So you get there immediately at this probability is a summation from k equals 1 to n, probability of A conditioned on bk times the probability of bk. The total probability theorem is very useful and has many applications, and we will see that there are many scenarios where you would know the conditional probability, A conditioned on things, but you don't know the probability of A itself. You know the probability of A conditioned on certain partitions, and you know the probabilities of these events constituting the partition. So you use both of them combined to get the probability of A. Everybody's okay? Awesome. Let's do an example, example 2. So for these examples, you have them, especially the ones that require a lot of writing, you have them in the notes. I'm just gonna write like the main ideas for those who don't have. How many of you don't have the notes, either printed or on your tablet or cell phone? 1, 2. Okay, I didn't see you. No, just kidding. So, okay, I will write like the fundamental points about the problem, and we'll discuss it together. So you will not miss anything. So we have an urn, and that urn has 2 black balls, 3 white balls. You select 2 at random with no replacement. And you note the color. Note the color. What is the probability, or find probability of B2? Second is black. How could we do something like that?
Result of first white then black plus both blacks.
Good. How can you decompose this immediately into conditional probabilities?
Yes.
Good. Let's do that. So probability of B2 black, you are saying is probability B2 given white 1, right? Probability of white 1 plus probability of B2 B1 probability of B1. There is a simple tree for that. This is black on the first, white, black, white, black, white. We already know the probabilities on these 2 branches, 2/5 and 3/5. Can someone help me with these 4 probabilities from left going forward? What is this one?
1/4.
Thank you. So 1/4, immediately you realize this is 3/4. How about this?
2/4.
Thank you, exactly, 2/4 and 2/4. Now, it's a matter of simple substitution to give you that the probability of B2 is 2/5. All right, good. Now we move on to also a very important rule, which is Bayes' rule. Bayes' rule. So we stick to the same partition we discussed before. It tells that the probability of Bj conditioned on A is the probability of A conditioned on Bj times the probability of Bj divided by summation from k equals 1 to n. Probability of A conditioned on Bk times the probability of Bk. Good. Why is this equal that? What is this denominator?
Probability of A.
Thank you. It's probability of A, and the numerator is the intersection, so it is easy to see why this is happening. Okay? Again, when is this useful? And we will do a very important example right now. It is when you do not know the probability of Bj conditioned on A, but you know the conditioning or the other way around, and you can use it to get the final answer for Bj given A. So you don't know Bj given A, but you know A given Bj, and you know the Bjs. All right? Is there a situation like that? Yeah, way too many situations. Let's do this example, example 3. We just talked about the probabilities of what was transmitted being something, and we called it the priori probability. And now we will talk about the posterior probability or posteriori probability. Posterior probabilities. let's refresh in our minds the wireless communication models we had. It has an input on one side, and that input was essentially A, and we had this one being B. We had A0 for the 0, A1 for the 1, B0 for the 0, B1 for the 1. What is the posterior probability? The posterior probability is essentially the main problem of these systems. You are standing here, you have something in hand, which is what you receive, but that's not what you want. You want to know what was transmitted. That's what you want to know. So essentially, this is the problem of all these systems. You sit here, you have an imperfect channel, something transmitted, data corrupted. You want to know when you are here, what was transmitted here. So what is the posterior probability? That's exactly what we're trying to find. Find the probability of A0 given B0 and the probability of A1 given B0. How can we find the probability of A0 given B0? That's where the magic of Bayes' rule comes. Is that you use the other conditional probability you know and the probability of the data transmitted in order to get this probability. How can we apply Bayes' rule here? It's going to be the probability of B0 conditioned on A0 times the probability of B0 divided by. So it's B given A times B over the probability of, my bad, this is A0 over the probability of B0. Right? This one is the intersection and this one is B0. Basic conditional probability, and that's Bayes' rule. Where is the trick here? How did Bayes' rule help us? We want the posterior probability A0 conditioned on B0. We know B0 conditioned on A0. These were the probabilities at the edges we have already discussed. And we know the a priori probabilities, the probabilities of A0 and A1. You use this one and this one to get this one and thus get this one. Fine? How can we get this one? Let's write the other equation first and then we will ask the question. How can we get this guy? Probability of B0. Total probability, thank you. So we do this through the total probability. Probability of B0 conditioned on A0, probability of A0 plus the probability of B0 conditioned on A1, probability of A1. And this thing ends up being 1 minus P, 1 minus delta plus P delta. Good. The rest is stuff we already know. We will make some substitution. I want to ask another fundamental question before we move on from the Bayes' rule and the posterior probabilities. And that fundamental question is, when you have the most trivial receiver ever, what will you do with these probabilities to take a decision? So we are assuming that you are not performing any coding, any advanced signal processing. You're not doing anything fancy. You are just sitting at the receiving end, getting two probabilities, making a decision based on these probabilities. How could you use these probabilities to make a decision about A? What would you do with these? One over?
1 over 2. You could go like it's either right or wrong. If the data be transmitted.
In this system, you will never know whether it is right or wrong. I mean, you could know if you have a third level that is called erasure. And then once you get erasure, oh, you know it is wrong now. But in this system, you will never know. It's just you will take a decision to the best of your knowledge. And we are assuming that your system is not sophisticated. You will not be coding. You will not have some signal processing at the transmitting end, some signal processing at the receiving end in order to improve the reliability of your system. You're just sitting here and taking a decision. How could you use these two probabilities to take a decision?
The higher probability.
Exactly. That's the most, yeah. That's what you do. So you just like compare these two and take higher. There is a concept called the likelihood ratio that essentially goes in line with that, which is just that you divide them and see whether you are greater than 1 or not. And then there is another concept, because you know on the implementation end, it's much harder to implement multiplications and divisions and much easier to implement additions and subtractions. So there's something called the log likelihood ratio. So you divide them and take the log. And if your log is greater than 0, you take a specific decision. Less, you take the other decision. Clear? Awesome. Okay. We will do now independence of events very quickly. A and B are independent if the probability of A given B equals the probability of A, or the probability of their intersection is their multiplication. And then for a three-tuple set of three-tuple events, you have the probability for 3 events A, B, and C. You have two conditions: pairwise independence and in addition to that, the probability of A intersect B intersect C is PA, PB, PC. Intuitively, this sounds pretty logical, right? When you think about this, two independent events, A and B, you are checking out the probability of the first happening, condition that the second happened. They are independent. The probability does not change. And thus, the probability of the intersection is the probability of the multiplication. This one is a little more advanced, that it has two conditions. Okay? Some note before we move forward. What if you have conditioning on more than one event? So you have the probability of A, B given C, and the probability of A given C. So let me do the first, and then you will help me with the second. It is the probability of A conditioned on B and C multiplied by the probability of B given C. Okay? How can we do the other one using the total probability theorem with conditioning? Let's write the summation over K. The probability of what times the probability of what? It's just right there. It's A conditioned on BK and C, BK conditioned on C. All right? Okay. Let's now do some combinatorics. For combinatorics, you have seen all of this since high school. I mean, you are pretty aware of this since high school. So today, what we are trying to do is to give you like a different perspective about them, like to think about them differently, to try to connect them. Counting methods. First, you have sampling with replacement with ordering for n objects and k samples. How many options you have here? Number of options. A set of n. You are choosing k times. You replace, and ordering matters. What is the number of options here? This is the easiest one of them. N to the k. Correct. Sampling without replacement, but with ordering. Number of options. So here what is happening, every single time you reduce the number of options by 1 because you don't replace. It's without replacement, but ordering matters. What is the number of options here? And permutation k, NPK, correct. NPK, which is factorial n over factorial n minus k. Sampling without replacement, without ordering. What is the number of options here? Now, ordering doesn't matter as well. Good. It's n choose k, which is factorial n over factorial k, factorial n minus k. The relation between these two mathematically is obvious. This thing is this thing divided by factorial k. Why? Exactly. Thank you. So if you have k objects, the total number of permutations you can generate for k objects is k factorial. All of them should be treated as one option, right? Number of permutations of k objects is factorial k. And the last one, which is the most tricky one, sampling with replacement, without ordering. So the number of options here is n plus k minus 1, choose k. What is the logic behind this one? This one is a little tricky, and we will do it through a separate example right now. It is essentially that it's as if you are doing a combination, but you get k minus 1 additional options. From where those k minus 1 additional options are coming? From the possibility that you can repeat your choice every single time. You can repeat your choice. You have a repeat choice. Okay? But you cannot do it k times. It's only k minus 1 times. You cannot repeat your option the first time. It's the first time you are choosing. But you can repeat it on the second time, the third time, the fourth time, until the k minus 1 time. Correct? Good. Let's do an example on that. So there exists k minus 1 additional options. But before that, why can't we get this through permutation? Because ordering doesn't matter. Okay? Let's do an example that really fits into this and could help us see how it works. You want to partition a line with 4 segments into 2 to 4 segments. So it has 4 original ones, and you want to partition to make cuts into 2 to 4 different segments, distinct segments. By picking 3 cuts. Cuts can be repeated. And the question is how many arrangements? So that's our line. It has A, B, C, and D, 4 different segments, 3 places to cut, say 1, 2, and 3. And you want to cut this thing into a number of segments between 2 and 4. What is a possible 3 choices? What is a possible 3 tuple choice that allow us to partition into only 2 segments? Remember, cuts can be repeated. Where shall we cut 3 times on this thing such that we separate into 2 segments? For example, what can we do to separate into this thing? A alone, B, C, and D alone. 2 segments. A alone, B, C, and D alone. What is the possible cut we will choose? Yeah. But then you choose 1 3 times. That's it, right? So 1 1 1 gives you this thing, right? Can someone tell me a possible cut to give us 3 instead of 2? 1 1 2, 1 2 2, right? You repeat only one of them. And so on and so forth. So you could notice that there is some combinatorial term that could be applied directly, but in order to understand the logic, we will try to do it step by step. So solution, let's do all the possible options. First, you can pick 1 or 2 or 3. If you pick 1, after that, you can pick again 1 or 2 or 3, right? At this point, right? But we will call the 1 1 thing R1, which is repeat the first one, all right? And then it's R1 or 2 or 3. If you pick 1 followed by R1, what are the options and how many options do you have next? You can repeat again, or 2 or 3, right? So R2, 2, 3. How about if you get 1, 2, and remember, we do not want something that bobs up again that we have already shown, because ordering doesn't matter, right? If you pick 1 followed by 2, what are the available options to you? So the available options to you are R2, 2 again, or 3. Remember, you said 1 here. 1 2 1 is itself 1 1 2. Right? So 1 isn't a choice here. It will appear to be something that you have already seen. Good? So yeah, the only 2 options you have here are R2 or R3. How about if we pick 1 followed by 3? What is the only option available? Exactly, 3 again, which essentially is R2. No, it cannot be like if you pick here 2, it would be something you have already seen before, right? Because it will be 1 3 2, and this is 1 2 3. It's the same thing. Good? Now, could someone help me with the 2? First, you have R1 or 3. For R1, what are the options you have? Exactly. R2 and 3. And here you only have R2. And then the last one you will have R1 and R3. How many of these options do we have? What are these arrangements? Yeah, just counting them. They are 10, right? We have 10 of them. which essentially could have been by noticing we apply this directly. So ans is n plus k minus 1 choose k is 5 choose 3, because here you have 3 and 3 and 3, which is 10. All right, let's do one more combinatorial example, will be the end of today's lecture. Second lecture. So you have n balls labeled 1 to n boxes labeled 1 to n. You are putting balls into boxes randomly, with the feature that every single ball has an equal probability to go into any of the boxes. All right? Find the probability that after arranging all your balls, A, box 1, and possibly others, empty, exactly one box empty. So first of all, let's start with the easiest thing, the denominator. The denominator should always be the total number of options you have. What is the total number of options you have in an experiment like that?
N over S.
N over n? Over? What do you mean by over? N over n equals 1. N to the power of n.
Oh, okay.
Okay. Yeah, you're right. This is not an English lecture. That's what you meant. Is that clear, right? You have all the options available. You can put all of them into the first box. You can put all of them into the last box. You can arrange them any way you want. How about the numerator in this one? Yes, exactly. So remember that always here is the total number of choices you have. Right? You just want to avoid box 1. That's all what you want. You don't care what happens after that. You can repeat 2, you can repeat 3, you can repeat any of them. So this one, as our friend said, is like that. How about B? Denominator does not change. But before putting some combinatorial terms in the numerator, let's decompose this thing into a series of events. You want exactly one box being empty. For that to happen, what are the events you need to have? Hint, there are 4. There are 4 of them. What are these 4? You want one of them to be empty. Exactly one.
One box should have 2 balls.
Awesome. Great. And the trivial one of them would be empty, mentioned in the problem. And then you have 2 more. One box having 2 balls, one box being empty, and then 2 more things. Because these 2 are not enough. You can have one box having 2 balls, another box empty, and then possibly others empty.
The rest has 1 ball.
The rest has 1 ball each, correct? And then there is one little event missing. Remember that the balls are labeled. Okay? Remember that the balls are labeled. So, what is the 4th event? Let's write that the other 3 we had until now. So 1 box empty, 1 box with 2 balls, n minus 2 boxes with 1 ball, and what? Exactly. And then picking 2 balls. Because balls here are unique. You need to pick specific 2 balls, right? Picking 2 balls. Good. It's just one step away from solving this problem. Number of ways of picking one box being empty is? Yeah, exactly. It's as easy as, don't think about it as a tricky question. How about this one? One box with 2 balls. Yeah, you took one away. It's as simple as that, right? How about this one? N minus 2 boxes with 1 ball each. Exactly. But since you will exhaust all of them until the end, and you took the 2 balls, it's n minus 2. Permutate n minus 2 again, so it's n minus 2 factorial. Exactly. And the last one is simple, n choose 2. You multiply all of these, n minus 1, n minus 2 factorial, n choose 2, that ends up being factorial n choose 2 over n to the power of n. So this also tells us something about this feature of decomposing the bigger events in order to calculate probability. Any questions? Everything is good? All right, thank you so much. That's all for today, and see you on Thursday, inshallah.